Now we're going to talk about how we do operations, that is addition and multiplication with floating point numbers, and we're going to talk about the loss of precision that can happen because we can't represent both really big and really small numbers at the same time with floating point. So let's talk about addition. Here's the example we're going to look at. We're going to do 2.1 times 10 to the 12th plus 9.2 times 10 to the 10th. So in order to do this, the first thing we need to do for addition is get the exponents to match. So how do we get the exponents to match? Well, 9.2 times 10 to the 10th is the same thing as 0.092 times 10 to the 12th. So we basically shifted this over to increase the exponent. Now we can go ahead and add the mantisses. We can add 2.1 and 0.092, and the exponent is going to be the same. So this gives us our result. Now we round this to fit in the number of bits we have, and there's our answer. So let's take a look at the example here. So 2.100 times 10 to the 12th, we've shifted over the next part, the 9.2 times 10 to the 10th, and by shifting it over we get the same exponent, so now we can simply add up the mantisses and the exponent stays the same, and we round it. So what do? Shift to match the exponents, add the mantisses, and round to fit in the bits. This is a lot more complicated than integer math. So integer math, you just add it up. Here we have to do the shifting and the adding and the rounding. And we may lose precision. So if you look at what happened here, we added 0.92. So here's the 92, but we didn't even see that in the final result. The final result went from 2.1 to 2.2, yet we had 2 digits of precision here. So we lost some of the precision of this value when we added them together. How do you do floating point multiplication? So here's the example we want to look at. 2.1 times 10 to the 12th times 9.2 times 10 to the 10th, same as before. So we simply multiply the mantisses, add the exponents, and round the number. So much simpler. Have the two values here. We don't need to adjust the mantisses because we're multiplying. We do the multiplication and do an addition, and then we round it. So multiply, shift, and round. So this is much simpler than floating point addition. There we had to shift the numbers beforehand in order to get the mantissa to fit. Here we just go ahead and do the multiplication and then make sure we end up in the right normalized format. So if you notice here we did the multiplication, we ended up with 119.32, and if we wanted to have only one digit before the binary point, we'd have to shift it over to make it normalized. So even though this is simpler, we still need a big multiplier. So we need to be able to multiply the mantisses. We talked about how there were 23 bits for the mantissa, so we need a 23 by 23 bit multiplier. Now how can we lose precision when we do this? So let's take a look at this. How can big plus small ever not equal big plus small? So in this case, if we have a big number and a small number, what we're going to see is that if we add the big number and the small number, it's about equal to the big number. Let's take a look. So we added 2.1 times 10 to the 20th, and now we're going to add it to 9.2 times 10 to the 5th. So this number is enormously bigger than this number. And in fact, this number is a 10 to the 15th difference, or a quadrillion times larger than that one. Enormously bigger number. So in order to do this addition, we need to get the exponents to match. So we put all these zeros in front of this value, and now we're going to add 2.1 to 0.0000000000092. Well, we add those together and the answer is 2.1 because we don't have enough bits to represent all of this. So we just added a big and a small number, and the result we got back was exactly the big number. So this is because we did this shift and we didn't have enough bits to keep track of all the data. So that 9.2 times 10 to the 5th that we were adding in just disappeared from the result because it was so much smaller than the big number. This is the problem. We can't have a floating point number that represents both really big numbers and really small numbers at the same time. So what happens if I do this math and then I subtract out big in the end? Do I get small back? Well, so here's the question. What does big plus small minus big equal? We just saw up here that big plus small is big. So big plus small is big, so big plus small minus big is going to be big minus big, or 0. That's not what we expected. If we write out big plus small minus big, we expect to get small out. We expect this big subtracted to cancel out that big, but instead we're getting 0. So getting something close to 0 is not good. What if we were to do some division with it? And the reason we have this problem is we have this nonlinear precision. We can't represent both small numbers and big numbers in the same floating point value. So if I do this computation and then I divide by the result, well, now I've got something divided by 0, and we all know that dividing by 0 is a big no-no. So the order of the operations matter. If I had written this equation differently, if I'd written as big minus big plus small, then I would have gotten small back. Because here I'm doing math on two big numbers and end up with something small, 0, and then I add that to another small number and I can keep the precision of the small number. So the order of operations matters with floating point math. This is really hard to do right, but the good news is everything you care about has already been done for you the right way. So if you need to do matrix multiplication or floating point or fast Fourier transforms, people have figured out how to make this do the right thing. So don't ever write your own algebra library to do stuff on a computer because you're going to make a mistake here. People spend a lot of time thinking about the right order of operations. So now let's review what we have here. We talked about non-integer numbers. Talked about two types, fixed point, where you put the binary point in one place, and floating point, where the exponent chooses where the binary point goes. Fixed point is just like integer math, but you specify how many bits for the fraction, and this is great if you know the range of the numbers before you start. Floating point, the fractional point, is determined by the exponent, and we have this mantissa, an exponent, and a sign bit. And these are things which allow us to adapt to different types of numbers. So we have this nonlinear scale. That is, we can have small numbers and big numbers, but we can't have both. We saw that addition is complicated, how we have to shift the exponents to match before we add them. Multiplication is reasonably simple. Division is horrible, and even on computers today, division will take 7 or 10 times longer to do than multiplication or addition because it's so much more complicated. And we saw that if you combine large and small numbers, you're going to lose precision. So the real truth here is you've seen a lot about floating point numbers, but there are a huge number of nasty issues. So floating point numbers represent not a number, and they represent infinities and negative infinities, and they're non-normalized numbers that you can use, and all sorts of nasty stuff that goes on here. And if you're interested in it, you can go read about it on Wikipedia, but this is something that's really best left to the experts. And this is why nobody tries to invent their own floating point number format anymore. So question, how are fixed point numbers spaced on the number line? We saw how floating point ones are spaced. How are fixed point ones spaced? So fixed point numbers are spaced linearly. They're the same space apart. So here we go. We've got a fixed point number, and here are the first four of the fixed point numbers, 0, 0.125, 0.25, and 0.325, and they're each 0.125 apart. So for a fixed point number, the step between each numbers is the smallest number, or in this case, 00 binary point 001. In floating point numbers, the step between each numbers depends on what the exponent is, and so it's different for large numbers and small numbers, and that's why you get that exponential distribution. Question about losing precision. Which one of the following here will not give the result specified? Well, here the problem is the big plus small minus big. This is what we saw before. When we subtract off the big here, this small is going to go away because when we added the small to the big, we lost it. So big plus small is about equal to big. We saw this before, how we had this number with this that was much, much smaller,